Welcome to the Ropecon session on supercomputers and artificial intelligence in reality as story elements. My name is Pekka Manninen, and with me
Maarja Bussov.
And what we're going to do today, slides working, is to first discuss supercomputers. You know, the room-size computer engines and the machines familiar from reality and from science fiction. And well, in the beginning, we're going to talk what they are in the real world. So they're a little bit of their history, what they're good for. So why do people build supercomputers in the like a real present day world? So what can you do with supercomputer simulations, and what you can do with extreme scale data analysis in furthering science? And then some glimpses from past, present, and also future. What is there what is there at the moment and in the future?
And I will be talking about artificial intelligence. Is there some autonomous intelligence designed making decisions for us? And what's the real reality of AI? And what does AI mean to people who work in machine learning?
And the third part, we'll going to go to the Ropecon team, so just have an interactive discussion and some ideas, followed by discussion on how could these teams, meaning big computers or supercomputers and AI, be employed as story elements in either fiction or in role-playing games or other game design. And perhaps a little bit of a report here, so who we are for talking about these things. So I've got a scientific or like a researcher background in computational physics, but I've been working for the last 13 years or so on the infrastructure side. So I work at the Supercomputing Center in Finland called CSC. And I'm currently the head or the director of the LUMI Leadership Computing Facility. That's the home of the European Union's upcoming flagship supercomputer called LUMI.
And I am working in Helsinki University in research as a postdoctoral researcher. But I have a very mixed background. So my main subject would be mathematical statistics. But then I went for PhD working with physicists, cosmologists. And now I'm working with plasma physicists and applying machine learning and statistical modeling for their research questions.
But I want to still stress that we are here not to represent our employers, but give it this as just private persons and a fellow gaming geeks. And hence we are not using some random PowerPoint template and then not our institutional PowerPoints. And basically everything we say are just there. Some things may be opinionated, but it's just like our own opinions on different topics. All right, and then some practicalities. So we would like to get this interaction. I know I would love to be in Messukeskus with you to in a real meeting room, but let's try to make our best for the and the current circumstances. So. Please do write questions to the chat. So I think I will see them on the screen here. I can take them either at the end of the talk or each of these three parts, or we can take them at the end. Or if there's something that's kind of like an urgent, feel free to put it there, and I will either have it on the fly or then during those kind of breaks there. So I think we'll go to spend something between 1 hour and 1.5 hours here, depending on the amount of discussion and questions. Okay, let's get going. So supercomputers and supercomputing. And the kind of underlying reason for building big computers in a modern day world is mostly driven by science. So our journey and aspiration to understand the fabric of reality, and from this understanding to make something that's useful for the whole society. And the three pillars of how do we make new insights, new information, how do we explore this fabric of reality is doing theory, building models, doing experiments to either verify the models and then use theory for interpreting the experiments. But the third pillar has been for more than 2 decades, perhaps 3 decades, have been computing, because everything you basically can count on a paper and pen has been counted. So there's no basically new. So the computers have been there for decades now to really make these equations and these models to fly, and to be able to have the data from the experiments to be analyzed, verified, simulated, and so on. And the reason for building ever bigger computers have been for being able to carry out this question to ever more complex circumstances and questions. And a supercomputer is a scientific instrument, corresponds to a telescope or some kind of a particle accelerator or some kind of a measurement device that are built roughly on the same components as the computers as we know on our working rooms and living rooms. They do have memories, they have processing units, they have hard disk drives and so on, but of course they are not computers in a sense that they are not good at where the personal computers are good at. But at the same time, they are good at something that the personal computers can never do, which is of course the amount of number crunching they are able to do. And the purpose and the motivation for building this room, computers larger than my living room, is to be able to tackle the next level of scientific modeling questions. And then they are useful for some time. At some point of time, they have a sort of everything has been counted that you can compute with those. And then you kind of need the next generation of the systems, and this is always the kind of a vanguard of scientific computing. So the biggest computers are there for doing something that you cannot just simply do with any smaller computer and a less powerful computer. And there's no kind of a clear definition what is a supercomputer and what is just like something else. But one kind of an indicator is this kind of a listing of 500 fastest computers in the world is called as top 500. It can be a kind of an indicator or some kind of a relative list, but meaning that there's a kind of a fixed number of supercomputers in the world at the time, but of course the supercomputer of a couple of years ago is maybe outperformed by much kind of devices today that are kind of a much less impressive. And idea is here is that, like I said, they are built roughly on the same components. So kind of they are motherboards and they are memory DIMMs and they are processors. And the idea is just like there's no kind of one single super processor, but you put a lot of those and make this kind of a fabric around them to interconnect these different small pieces in a way. And just building faster of these building blocks and tighter interconnects and just like a scale out is the way for supercomputing. And the history of supercomputing starts somewhere on already in the Second World War, where the first mechanical devices for cracking cryptography messages were kind of like a predecessors of computers. And in the Cold War time, well, at least the most heaviest or the most metal, in terms of footprint and the weight and everything, was something called SAGE that was meant for the US airspace monitoring. So whether the Soviet Union missiles are now approaching the US or not. And this system, known from many pieces of fiction and movies, did really exist between the late 50s to already to early 80s. It was based on several buildings full of computer racks and command centers, and also had a first motivations towards internet and connecting machines to each other. So having a role on a generation of the ARPANET, that is kind of like a prehistory of internet. But also from the civilian purposes, so the university started building their own computing centers in the late 50s and early 60s. One of the most famous ones were called Atlas in University of Manchester in the early 60s. Also, Finland got its first computers around that time, called ESCO, was the first computer system in Finland in the early 60s. And the commercialization of the supercomputers took place in the early 80s by a computer company or vendor called Cray that started building this kind of like a sleek looking something that somebody could just go and purchase and not have to build it yourself, and kind of like a not unique design every time, but kind of like a productized machines. And supercomputer progress have been tracked systematically from the early 90s with this top 500 list, and it's been, as you see from here, it's like a logarithmic scale. It's like a line, like a straight line, so it's exponential growth, and this is one of the kind of most accurate realizations of the Moore's law, where the computing power doubles after every some interval. So this is the fastest system in the world. This is the number 500 in the world, and this is the sum of all 500 computers. So you can also see how big the number one system is, if this kind of not that far away from the 499, the sum of the all computers at the same time. So it's released every half a year. So the last one is from this June, and the number one is here, has been out 3 times in a row. It's called Fugaku in Japan, and it's capable of doing something we call petaflops. So it's 442 petaflops, meaning 4 times 10 to the power 17. So a bit less than or 1/2 of 1 million billion operations, so meaning additions or summations in a second for a single given computing task. And this is just like a solving linear algebra problem. This is the high performance lean-back benchmark. Of course, cannot miss the opportunity of having a little bit of fairy dust here. So currently, the fastest supercomputer in Finland is called Mahti. It's a rough. It's below 10 petaflops in lean-back. But what we're going to see in next November is an entry of the LUMI system to the top 500, and the commitment for LUMI is not, it doesn't fall not that much below the Fugaku, and this is already twice as much as the number 2 in the current list. So I think we're going to have a top 3 or top 5 entry also in Finland. But this is not the Finnish system, but this is the European Union's flagship supercomputer that was decided to locate in Finland, in Kajaani in Finland. And what does this mean in terms of computing power? So present day, the most powerful laptop you can buy from the market would be somewhere 150 teraflops, 120 teraflops on the lean-back performance. The same benchmark if you run it on buy as fast laptop as you can and run the same lean-back. So it's an one order of magnitude. So it's basically it's not that far away from the well, it's still let's make it 10 times, 20 times slower than the last ones in here, but there's already like almost 4 orders of magnitude, so 10,000 fold, or even no, I was doing something wrong. So yeah. So some like a different difference of 1 million already to the number one systems. And I once calculated that the LUMI would correspond and computing power of 1.5 million latest laptops, and it would be a tower of more than 20 kilometers high if you would generate those with laptops. So what it does mean in the applications, so how the history has gone is like I said, it has a kind of like a military background. So from the Second World War innovations to and the army has been once you had the resources and the motivation to build the computers, but at the same time physicists, mathematicians, chemists found those computers useful for computing their integrals, what they had on their scientific challenges. And as the time progresses, there's also commercial applications on the commercial side applications, and kind of like as the computers get more like a common and affordable, more and more areas find kind of a use on them. And this same applies throughout the decades, with the last decade being the more and more communities sort of like a benefiting and then finding the tip of the iceberg computing, with the trends on this decade, on the last decade, have been on simulating, trying to simulate a human brain, modeling full like a human organs on molecular level, high frequency trading, so the kind of a buying and selling stocks in a kind of a very automatized fashion, search engines, and of course something we called deep learning, that's kind of a heart of the artificial intelligence. And perhaps this decade we'll see lots of this kind of digital twins, so we can build models so complex that we can like do this approach digital twins of a human body or a say globe. So the destination Earth is a kind of like a very big project of European Union to go so deep on the Earth system modeling that we can start asking what if questions from how to tackle the climate crisis and so on. In the future, we are going to see in supercomputing, well, more of the same in a way that I think there will be this kind of just like a evolutionary trend going on. More slow will end at some point of time, but at the same time, there will be new memory and processor architectures that will be used for supercomputing. Accelerators known as the GPUs that we know from the graphics gaming is something that most of the fastest supercomputers, LUMI included, are based on, and they will be a very big role on the fastest computers. And also on the below the top 10 computers, we will see more specialized system for a single problem or scientific domain, more specialized ones. There will be new computing paradigms raising something called neuromorphic computing and quantum computing. And quantum computing is something that's a kind of an all new world. It has very little to do with computers as we know them. So they are not just fast computers, but they will be kind of like a all new paradigm. And the quantum computers very often encountered in different kind of board games and sci-fi series and sci-fi books and so on. So they are not sci-fi. You can buy one. You can just, if you have the money, you can go and buy. There are commercial quantum computers in the market at the moment. And the idea is to harness the quantum mechanical, so the microscale world for kind of like a faster solution of some problem. So the technology hasn't converged yet, so we don't know what's the final technology for this quantum bits or qubits, and we don't even know what's the kind of like a model is going to win here, whether it's an annealing or quantum gates or whatnot. So like I said, so you can go and buy a quantum computer if you have the money, and where the annealer technologies is kind of like a more mature at the moment. But basically, it won't remove the need of traditional computers at home or in the supercomputing facility, but it is a kind of like an accelerator for some fields, so quantum physics or combinatorial mathematics and things like this, where this kind of like a exponentially scaling complex problems are being encountered. Okay, so basically this concludes the first part for me. So wanted to just say that the fastest computers are something that being progressively built for the last several decades for cracking the mysteries what we have in science. And of course, I didn't stress it too much, but just like a very present day examples is that, for instance, we wouldn't be receiving our corona vaccinations at the moment without supercomputer simulations to understand the molecular, the atomic structure of the virus, to be able to sequence the virus genome and many. So it's like within one and a half years that we've been through this shit. So there's like there's hundreds and hundreds of papers about like important scientific contributions towards the solution of the pandemic that has applied the supercomputing in a way or another. So data analysis or simulation, molecular simulation, and everything in between and combined. And it's going to be so that every science domain will have their modeling and data analysis cases that cannot be done on anything that's at the moment presented on the planet, and hence there's a motivation for going this kind of like a Altius Fortius syndrome that we are doing, and it's just because that's how science works. And we have, of course, the kind of like a derived applications on the commercial side and also on the military part as well. And currently, the systems are reaching something we call exaflop era, where the computers are able to do 1 billion computing operations per second. And this ranges from this building blocks that have something to do with computers, but they are very tightly interconnected, and you can harness them to work on as one single computation. That's what I had in mind. So I would like to pause for a sec for questions or comments. So please type stuff to the chat, or I don't know if you can raise hand or give me this application. But so feel free to ask any questions if you have. Yeah, okay. Okay, at least I can't see anything on the chat. And I don't see any hands up. I hope you can access the chat and the
people are digesting the information.
But sure. Well, we have also time at the end of the talk. So also, if you come to something, that's okay. Something. Does it need a big maintenance team to keep a supercomputer running? Not per se. So we are talking about a handful of people, even for the biggest computers. So let's take it less than 20 to keep it running on the data center and the computer itself. of course, the supercomputing centers themselves have more employees, but we do need still staff to between the kind of like a researcher at the university and the computer, and to kind of like a map, do the kind of like a problem to solution style. So we need kind of like this kind of like application consultants even more than the system administrations. Then I have a question on how are supercomputers made? There are specific vendors that have specific factories for doing that, but basically the components come from the same places as the like processors and graphics processors, and then memories and hard disk drives come from the Taiwan fabs as for the PCs. And then the integrator basically buys them and then builds them to these cabinets of computers, and has their own IP there on the packaging and the interconnecting and so on. But like I said, they are like a specialized vendors for building and integrating those computers. And then are Cray systems still in use? Yes, the Cray itself has been acquired by Silicon Graphics in the late 90s. It re-established itself as a company in the early 90s. Was an independent company for years, delivering many of the landmark installations, and has been now some 2 years ago being acquired by Hewlett Packard Enterprise. And for instance, LUMI will be a Cray branded and a Cray technology computer, and there are many of the still landmark systems are still Crays. Okay, thank you. Very good questions. And like I said, I think we move on. As I spent my first half an hour, so
yeah.
I'll pass the floor. And
where is
yeah,
it?
It's just no.
Does it go?
No,
It doesn't. Do I need to click it towards your computer?
No.
Technical issues?
Technical issues. There it is.
Okay. Yeah. So I will be talking about artificial intelligence. Most of the talk will concentrate on machine learning, which is a bit like a broader sense of AI maybe, and what it's all about. And as saying, I'm not representing my employees in these opinions. So AI can be thought basically as deep learning algorithms. And deep learning is the case of having multiple layers of mathematical transformations. And these deep learning algorithms, as they make multiple transformations on the research question, they become very flexible and very precise classifiers. That's why they are applied to quite human-like tasks, such as vision or recognition or speech. And so you can also think of it as some kind of really complicated tasks that usually were solved by computer programmers, just writing some kind of instructions by hand. But the tasks are becoming so complicated that it's impossible to write them. So you have this kind of flexible algorithms that are more autonomous. And with these mathematical transformations, they solve these questions. So it's a very large class of problems that are being tackled with deep learning. And for having like a successful AI application, one of course needs the algorithms and which ones to use. You need to know which ones to use for your case. Good data sets, meaning that your result will be only as good as is your input data. Then you need the hardware, the processing units, the memory, and the computing power. That's the supercomputing that was just spoken about before. So these kind of methods or recipes or models are capable to resemble human-like intelligence, meaning that if you show a trained algorithm new images, it can detect the objects on the image and tell you that this is a cat picture, there is a man falling, there's a car, or they can even classify different satellite images. So if you have a high satellite image of a mountainous area, they can detect or distinguish snow from the clouds on the satellite images. Even in computer games, self-driving cars, and different alerts and diagnostics in medicine. And of course, electric grid management, optimizing the electric grids, or analyzing seismic data, giving alerts for possible earthquake risks. And of course, in social media, they give feedback and interaction. And of course, as I said before, this kind of like being able to optimize the use of energy in different facilities, this kind of optimization can be done with AI and is done. So machine learning is basically a set of algorithms that are able to make a lot of small decisions for you. So the labels are very often used as this kind of like a distinguishing factor in machine learning. And what do they mean is that labels are the outcome what you want to get. So if I show a cat picture, I want to get labels of a cat or a dog or a horse or such. So the algorithm, the machine learning algorithm, labels new data. So it was trained on already labeled images, and now by creating this recipe, it's able to label new data, new cat and horse pictures. It basically, the algorithm just stitches together this kind of a recipe that was trained on the input data. And here you see this kind of a flexible net on the right-hand side. And this is a GIF of a self-organizing map at work. And self-organizing map is an artificial neural network. It is basically a layer of neurons. All of these black dots are neurons. And the neurons in the beginning don't know anything about the input data. They have some kind of preliminary information that can be given in either that can be given randomly or can be given a little bit more sophisticatedly. So how intelligent your neural network in the beginning is depends on the initialization of the neural network. And then you put this algorithm to learn from your input data. And the input data are these orange rectangles here. And then the neural network starts to learn and tries to mimic the distribution of the input data here. And you can see that the network is kind of stretching itself out in these three directions towards these three different sets of the data of objects in the same data. So these three different sets are different clusters. We name them as clusters. So this assignment here is basically you have this input data, all of these orange boxes, and you want to detect which kind of orange boxes are similar to each other and which definitely aren't similar to each other. So you want to detect clusters. And with this flexible map, you can train it to kind of detect these different clusters. And in reality, of course, these orange clusters don't exist only in this two-dimensional plane here. They have higher dimensions in reality, many, many variables that the neural network is learning from. And the neural network neurons here, the black dots, as well have many, many different weight components. And in the end, once you have stretched out this neural net, you can apply this stretched out recipe kind of to new data. And then the new data will be automatically classified to belonging into these three types of different classes or clusters. So this is a self-organizing map. It's not a deep learning neural network. It's an artificial neural network that basically consists of only two layers, the input and the output layer. And this is a simpler case of neural networks. And so for using machine learning, we use one of the most important things is, of course, the information that is available for you for training, and then choosing the algorithm. And as a result, we want to obtain this kind of a recipe or a model that's able to detect the same structures from new data that we don't have knowledge about yet. And there's many different types of algorithms in machine learning: linear regressions, k-means, random forests, neural networks, and etc. And this is on the right-hand side, just an example of a self-organizing map. And next, just two images as well with like this kind of user cases with data. On the left-hand side, let's see, we have two axes, x and y. There are certain variables there. They can be also linear components of variables in the data set. And we have trained quite a flexible algorithm to distinguish the orange from the blue type of data points. So this, we know that the orange belong to the orange cluster and the blue belong to the blue cluster. And now we have trained a recipe that's able to basically draw a border between these two different types. And now if we have a new data point, we put that new data point somewhere on this left-hand side x and y axes, then automatically we can color it orange or blue, dependent on which side of the line does it situate in. That's basically this kind of a recipe that classifies our data. And as you can see here, this line maybe is overfitted, which means that it is a bit too wiggly for the data case. And this, the outliers are also classified as the orange class. So machine learning is quite sensitive to overfitting and also overtraining. And on the right-hand side, you have another kind of a data case that I have been working with mainly is images. We have this kind of the blue, greenish, yellowish images, these small rectangulars here, represent the physical phenomena. And we want to detect different kind of structures from this physical phenomena. And we want to do it automatically because we have huge amounts of data and no one wants to go through this data by hand and classify these circles from the lines. You can see this kind of maybe detect a little bit of this line-like structures, like worm-like structures, and then these like circular structures. So we train a machine learning algorithm that kind of tries to do this classification for us. And on this, on the pink, the blue, and the orange dots on the left under kind of like this kind of a triangle is one result of the k-means for this data. So the k-means has distinguished here 4 different clusters from this data, and the distributions are here variable by variable. But it is just to show kind of a representation of, we can put an image data in, which is of course not represented always as an image, but sometimes just like a 1D array of pixels with different variables, and you can train that kind of information with a machine learning algorithm, and then the machine learning algorithm distinguishes these pixels into different types of classes in the picture. So for having more or less a successful machine learning route is not always very easy, and it needs quite a lot of collaboration between the experts in the field and the machine learning experts, and then maybe even computing centers. But the most important thing always is to ask the right question. What do we want to classify? What is our quest in using the machine learning? And once you have raised that question, you need to have input data that really represents that. And it is general enough such that it is able to represent also future new data. And then next step would be to choose an algorithm that will then build this magical recipe for you and learn from the patterns that it sees in this input data. And after getting this recipe that is able to distinguish different classes or label your images, you need to test this recipe on new data and see whether it really works and how well it works. Because there always might be issues with the fact that the input data that doesn't really represent the whole question that you want to answer. So at the moment, there's many different applications in our everyday life that are using machine learning. Google Translator, different voice generating, speech editing. For example, when you write in your text messages, you have different suggestions for filling up the text for you. Vehicles are becoming more autonomous. Agriculture harvesters are getting more smarter and smarter, able to even give you advice as a farmer. Different personal assistants, social media and healthcare, and of course on marketing and sales. All these kind of design special adverts that we all get in our social media. So there's a huge tsunami of ML in commercial and research, both. Of course, research quite often tries to develop maybe more of the algorithm and maybe is less concentrated on just applying, but it depends on the field. And in research, for example, in physics, where I have been working in cosmology is stepping towards this big data science age. There's huge telescopes observing the night skies and giving us immense data sets. And this is a perfect scene for trying to and applying different machine learning algorithms. Or in space physics, for example, analyzing different simulations, because simulations with supercomputers produce immense data sets as well. And there's a huge tsunami of different kind of like applications in science coming up, and beyond physics, of course, as well. But my expertise lies in physical applications more. So as I spoke before, the input data is as important as the algorithm that you're applying and testing. So you cannot, if you train your algorithm, your machine learning algorithm, you cannot expect to get better results than you put in a way. So if in the first row, for example, if you want to train a deep learning algorithm able to detect school buses, motor scooters, and fire trucks, and the first column, sorry, not row, and you feed the data of images of these different kind of objects to your learning algorithm. But always the scooters and fire trucks and school buses are situated on the same angle in the picture. And the algorithm works very well with high precision. It always detects these three elements. But then you put in, after gaining the recipe, you put in new data. And this new data is not exactly the same data. It's a test safe data. It's a completely another data set. But in that data set, maybe not all the buses are exactly looking like that bus was, or they are rotated on the image. And suddenly they're not able to detect these objects anymore. As you can see, a motor scooter turns into a parachute and a fire truck turns into a school bus. So this kind of like the fact that the algorithms have also a lot of pitfalls or like weak spots that always needs to be taken into account, and choosing the right algorithm for the problem and having a quality and big enough data set for training the algorithm is important. And of course, you never know how well your algorithm or a recipe is working until you haven't tested it on new data sets. So yeah, just a little bit of remarks or kind of conclusions. It is a bunch of computer algorithms in the end that try to mimic human-like capabilities, meaning AI, and human-like capabilities being understanding text, voice, images, faces, etc., playing games. And of course, it is helping many science domains already as Pekka mentioned before, in developing the vaccine for the coronavirus. and of course also the models for climate change and how we can predict what kind of what will happen if we continue in our nowadays kind of systems. And this kind of universal translators are, I would say, quite here already, being able to, in my phone, for example, I just talk in English and it understands it in many different other languages and translates it immediately. Of course, the algorithms are limited and they are sensitive to different choices the analyst makes, or how the research question is set up, or how we can even what data represents our research question. So I would say that self-aware AI, in a way, as we would maybe imagine it as an autonomous intelligence being able to live as a human being, in a way, having memories, and is not reality. It is at the moment more kind of like a pool of algorithms that are being constantly developed and applied to gain recipes which are able to answer or simplify or classify human-like properties or qualities that we can do. It is not a sentient AI sitting in the corner and helping us live, but it is quite fine-tuned algorithms for special cases, what to answer. Yes, and that's it for me.
Let's leave this for a second. So let's take some questions or comments if there are. Again, feel free to type them to the chat. About AI in reality and where we are and in machine learning. So far. Okay, so we will get back to the topic then on the next part. Okay, and the third part, we get sort of like a little bit out of the scientist like a box here, and the change of the present day real world, and think about how we could employ these themes. So artificial intelligence, so like set aside the boring fact that they are fitting algorithms, or like a classic clustering algorithms more than like
some are clustering algorithms at all.
Like rather than this kind of like a self-aware beings. But let's set a little bit of the that aside and see what we can do is in fiction and especially in the role-playing games. And just some couple of examples from movies and TV. I guess everybody suddenly think along the same lines when hearing these words, and would be very interested in if somebody would like to share a lot of other less known examples. But just like saying what I want to kind of reach here is the as a story element is, for instance, on Star Trek that we all love is where the ship's computer, its capabilities, like the universal translator just mentioned, where the alien race just talks a few seconds and the computer builds a language model, and then you start hearing English from the loudspeakers, and or any other things related to the ship's computer, and it's kind of an AI feature. as well as the holodeck as this kind of extended reality is very important in many of the episodes. Also, it can be used as a villain, as in the Space Odyssey 2001 and the HAL 9000 computer that didn't turn out on a characters of its kind. The Matrix trilogy, where the whole kind of like a world was more or less like a computer-driven simulation, and of course the Skynet in the Terminator movie continuum, where they this kind of like a AI capabilities like started playing their own role and turned the autonomous machines against the creators. Or from literature, so the sci-fi literature was there when the very kind of like a first attempts towards computers were there. So Isaac Asimov had the multivac computer in many of the late 50s books. The kind of like farce of the Hitchhiker's Guide to the Galaxy had this deep thought machine built for a single domain to answer one very deep question. Of course, getting an answer that was a good example of this kind of like a being able to answer the right questions. So even no matter how big computer you build, but if you don't postulate the question in a certain manner, you will get an answer of the what your program is supposed to be doing. There are good examples on doing an AI in the early, already decades ago in the books. In the same fashion as the Wintermute. But then on the just to spark some discussion and ideas here. So how could we use these themes in role-playing game campaigns and stories? And of course you can think broadly, or in your fiction stories, or in even on board games or board game designs and so on. So something just like a pops up to my mind here is this. To let alone the fact that we cannot do a machine learning algorithm that would kind of reach this kind of a self-awareness in a sense that no matter how good chatbot you do and how well it kind of resembles a human discussion, it still doesn't understand to be doesn't have the knowledge of being a chatbot if you do it on current, as we know, as AI. And but here let's postulate a AI algorithm that's basically understands of being an AI, and it generates its own will in a way. So it has its own motivations. So it basically can be an opponent, it can be an ally, it can be a gray eminence in stories. And basically this kind of gives the game master a nice kind of a tool for addressing ethical dilemmas of like human rights and non-human rights, whether like AI is more intelligent than humans, are given the same rights from being not deleted from the hard disk drives as humans are, and they're just like slaves to the humankind, or can they have kind of rights of their own? So I think there's like a lot of like interesting and in a way important questions, because it's kind of relates to the like I don't know, humans like animal rights of the day. So that's kind of like one quick thought from my side, and like quite fruitful stuff for sci-fi, hard sci-fi, far future, near future. It doesn't really matter. So you can just like we can get the credible team out of it, whether it's just like a cyberpunk or is it something like a very fast-charging AI. It's just like a more capable AI and a more omnipresent AI. Of course, well, one thing I basically a little bit went too fast was the development of supercomputers. So there was the exponential growing curve. So let's see if I can mess this too badly or not. So this one. So if you follow back here, so let's say the mobile phone would be somewhere 10 times. The best mobile phones would be perhaps somewhere here, a bit lower. I don't know, 100 times lower than the best laptop. So, but if you trace back here, the capability of the late 90s #1 systems in the world. So this was the ASCII red called supercomputer in the States, in Los Alamos. They would be corresponding of a modern mobile phone with their computing capability. Also, even if you look at the laptop level, so 2005, I got my PhD in 2004, and then we was doing lots of computations for that one. So basically, I wasn't even using the fastest systems in the world, but the current systems back then would be comparable to the modern day laptop. So for the role-playing game here is that basically the current, if this was the 20-something years, 22 years. So the computing power of Fugaku and LUMI will go to your pocket in the 25 years or 2050. We would be talking about mobile devices that are able to do the stuff that they are currently the best computers in the world can do. So basically, this gives a kind of like a pretty cool features for this kind of like a role-playing gadgets in a way that if postulates the self-aware AI algorithms and but that would need a supercomputer to run them in the say near future world, it's still go a bit further and it's on a mobile device. So basically, it's a kind of not out of a just like a do sci-fi. Like long enough, it's basically means that you can have this kind of like devices that are self-aware in a sense. So having kind of like a Stormbringer of the in your mobile phone. Then the virtual reality, just simulation of the world. So just like having computer program that generates from a known rules and then starting points generates the kind of how something develops. And that's basically what the supercomputer simulations do and the supercomputer programs do. So this kind of virtual reality settings as explored in the holodecks and matrix and so on is a kind of it's a nice spice, or in a whole setting can be just like based on a virtual reality or augmented reality where you can play around with this. Also, if you do like a present day role playing, even like a give or take some tens of years, just like a narrative around information that we do with what we do on the supercomputing centers at the moment. So we could give like a nice starting points for stories. So for instance, what if the computers that mine those telescope data will find and clear evidence of messaging that doesn't arise from Earth? So how do we? What is their? What is the response and who knows about it and so on? Of course, this theme has been explored in many movies and TV series before. But I mean, you can kind of give this kind of a scientific flavor on that if you work on that role. But like I said, so there's like the telescopes and different kind of like measurement devices collect like a humongous amount of data. For instance, so something called square kilometer array is now being built on Australia. The radio telescope has like an extreme resolution of radio signals. So basically it can hear a mobile phone on the moon, and much further in fact. But as I said, there's the radio telescopes are very, very precise devices. So one of these computers mining the SKA data will find something interesting there. Or alternatively, we figure out that there will be an asteroid on a collision course. So how do we? What is the preparation for the and how many days before we know that and so on. And of course, something that unfortunately became story from a story to a reality is the pandemic style. So, like I said, the supercomputer simulations have been on a key role that we could some kind of hold on the pandemic. But of course, they can be different themes that we learn on those simulations. And what if we learned that the pandemic of that we have experienced wasn't natural at all, but some kind of a smoking guns point to somewhere, so you get a cool story around that one. So we find out something from the spread or from the virus itself that it wasn't there's something efficient on the outbreak. Or just there's a supercomputers being used for some sinister purposes. So somebody using them for designing new chemicals, toxins, viruses, or whatnot for extreme destructive power and how to counter those efforts. Also, one theme quite closely related to AI and supercomputing is cybersecurity. So it's how our privacy and how to put the penetration to the different digitalized world. So there's lots of themes to explore from there. Let me pause this for a second and see if there's anything on the chat that we could discuss. I think it would be very nice if people could speak up instead of chatting, but I think this is how we will need to do.
I can read your questions, you read my questions.
Yes, but I think there's something for you. There's a question for you, so I'll take this one first. The notion of human-like thinking, slow and fast, on the summary slide. So tell us more about that division and how it does differ from the intuitive thinking and the slow thinking things, and when if you reflect to the AI side, so how would you compare the machine learning?
I would compare slow thinking, meaning that we really take the brain processes information in a deeper level, and fast thinking, meaning that it's more a reactive response to your outside stimulus, like to what you see or what you hear. And I would say the machine learning or AI algorithms more or less at the moment are in this fast thinking. They're able to detect from pictures, from videos, they are able to help a car drive, detect danger, detect a pedestrian coming. You can that is something that you do while driving as a fast thinking. As well, detecting cats or doing some kind of speech enhancement in a way, as they do in our phones and laptops. So I would say majority of AI is this fast thinking, mimicking human fast thinking capabilities, not the slow thinking. Of course, mostly what AI or machine learning is developed for in science is to find something that humans weren't able to find from the data set before. So finding some kind of other hidden correlations that we don't know yet in the data. So as I showed you before, this image of this circular islands and the stripes, if a human looks at that image, they can very easily say, okay, this is that, etc., just by looking at the image. But underneath that image is very complex world of physics. and the world of physics that's not fully understood yet. Why do in reality, these sheets, these stripes are created there, and why do they break up? And what drives that? So we are hoping that the machine learning algorithm would maybe hint us to these unknown relations in the data that we don't know yet. So machine learning in a big sense is a helper to human knowledge and human detection capabilities. It's helping us to understand something that we are not yet able to understand in science, for example. And of course, in other fields, it can be used to kind of take the spot or to do this heavy duty work that a human usually does. So reading through different contracts and finding connections, you can have an AI algorithm that's able to highlight important things or write even up contracts for you. It doesn't need to be human work because humans can be applied on a higher level, on the more slower thinking kind of level of the process of the work. So there's different types of where AI and machine learning are important. But I would say in research, one of the most important places is for it to help us see some kind of connections we are not able to see by ourselves yet. Or then helping us manage huge data sets that we're just not able to analyze this information. Like as a humans, we need an algorithm to help us.
Good. Then there's a question for us both. So what are the coolest AIs in literature or movies in your opinion? So I think I would go for the Skynet, so as kind of archetypical villain where everything just like goes haywire.
Me, I need to think a little bit. If you can continue with the questions, I will think a little bit about this one.
Then just comment on so our smartphones do many things compared to all the like a sci-fi where you need different tools for different tasks. So yes, well, that's basically the gadgets and gear. So I mean, running an cyberpunk game in the 90s, they're basically the many high-tech theories is sort of like already like a bypassed by just any given mobile phone. So I mean that's kind of like a is the line here that predicting technology is extremely difficult, but kind of like a reminding this exponential growth there that the how fast at the end of the day the computing goes to the like the miniaturization and the kind of exponential growth of the computing capability, and this is something to bear in mind when designing the kind of a credible setting for the near future or far future, and what kind of things they can be in this kind of a handheld things. We have how does a sentient supercomputer express, I would say, AI, perhaps in this case? So how does a sentient AI express personality? Any examples in movies, literature, or games?
Okay, yeah, I can answer.
Yeah, sure.
Maybe my favorite will be Vision from the more in the Marvel series. The Vision from my favorite, because I just recently looked at WandaVision and I really enjoyed it. I would say that.
So if I would have a sentient AI, so I would express personality. So, but we have many examples in movies and literature and games, as we kind of thought, and quite often it's kind of like gives a fruitful story if it's turns bad, and the personality turns bad. But at the same time, it's sort of like as we don't have a sentient AI. So it's just like still a speculation and a fiction, work of fiction of what we do that. But like I said, so I say it's a fruitful story element in a sense that you can use it as an opponent or ally or just some kind of a gray eminence somewhere, and can be compared to an old vampire in a Vampire the Masquerade, or it can be just like a fierce opponent that has like a more like a different resources against you. But I don't know, how would you think? So I think it's the data that is being trained with that would determine the personality of an say AI.
There has been bad experiences with that one, hasn't there been? Was it an algorithm that was trained on internet? Basically, all the text that was in internet.
Yeah, I know that one story. And there's basically this.
And it ended up bad because the algorithm learns to mimic or learns to represent what the data had in his recipe. Kind of, if you talk to it, it has learned this magical, not really, but this kind of a model, what would be the most common or more frequent, or kind of what would be the answers. And internet is not a very friendly place. So it became very vicious, very, very fast.
Yeah, so there's a cool stories on this like the GPT-3 language network or the model is extremely good on kind of like a mimicking human-like conversation. So it generates on this kind of you type something, this kind of like a chatting. So it's like it generates opinions. So you can like discuss politics with it. But the problem is that those models have been quite often time trained with like a discussion board texts that tend to be kind of like a more aggressive than people typically are, and then you get this kind of a very cocky and very, very kind of like a vicious AIs in this. So it's very, I would say the personality would relate quite a lot how you train it's a kind of a tabula rasa, but you can generate and sinister or like a good-hearted AI.
If you put garbage in, you get garbage out. Yeah. That's kind of like still the rule of thumb. You cannot expect the AI or the machine learning to be anyway more intelligent or better than what you trained it with. It kind of represents still that the input data is able to represent the input data in a way.
And for instance, Microsoft had done like a Twitter bot that used reinforcement learning. This is a kind of like a way of training a data neural network that has this kind of feedback loop on things. And there were like a Twitter trolls just trained it to be a white supremacist in a matter of 1 weekend. So there were nobody watching the Microsoft Twitter bot started to put out like a white supremacy stuff on the Twitter feed. So by people knowing how to kind of like a poke that's so basically there's of course like a just not simple, but just computer programs without no kind of like a will of their own, but they can kind of still they sound credible, so they can generate credible looking thoughts in a way. But if you're talking about the like a real artificial intelligence that has the self-awareness capability or some to some limit, I would agree on that one. So it's really much how what is the kind of a content that we train it with. Again, I guess this comes to you and partly to here. How far we are from real AI if 20 years everyone can have a current day supercomputer in a pocket? And if we ever get one AI, is it possible to teach machines ethics and empathy to prevent Skynet happening?
Wow. Well, if everyone has supercomputers in their availability for developing.
But the idea was that basically you have in 20 years you would have like a LUMI computer in your
own computer. Well, I would guess to make that kind of a leap, there needs to be more this kind of mathematical development as well to the algorithms themselves, to the deep learning algorithms. And this is, of course, constantly done. And there are many pitfalls to deep learning as well. So it's not only you put your nice data in, you put the deep learning algorithm, crunch it on a supercomputer, and then this nice little recipe solves all your problems. It's quite a long journey to get to something that really works. And I think that sentient, there's a question, was sentient AI? Or...
No, but it just don't, choose whether you want to have this like a self-awareness or not, but just like have a like a AI. It's as a, like a neural network, so you can be like a teach ethics and empathy for the AIs that do the decision making.
I would even think maybe some kind of ethics and empathy can be fed in a certain manner, or like this kind of feedback, or this kind of training the algorithm knowing what's right and wrong in a way. But I wouldn't go as far as saying that it would be like a human-like behavior of an AI, or it would be self-aware in a way in 20 years, because the algorithms are still mathematical transformations in the end. They're nothing beyond that. There's no chemicals, no biological systems connected to it. So that's all cut out.
Yeah, and even if you train an AI to mimic emotions, they are just the expressions of emotions used in the places where they're being used in, but they don't kind of emerge. There's nothing emergent basically. But that's one of the kind of take-home messages from the current day AI, that there's no kind of like an emergent behavior, but everything is in the data that is being trained with.
And I want to bring out that yes, computing power is very important for developing AI, but there's other aspects to it. So just having a huge computer doesn't give you the ability to create an AI. You need the data, you need the research, the questions, you need the algorithm, knowledge how to use it, and sometimes even development of algorithm. So there's many different ingredients to the pizza or the soup or what you want to create.
Okay, this is a comment on just the question, but a comment. So more examples on the literature ones. Thank you. So coolest minds in literature, Ian M. Banks and the culture. Newer interesting books and book series that explore the idea of what is humanity and personality. Bobby Verse, Motorbook Diaries, and Imperial Lodge or series. Thank you. I'm a little bit of illiterate on this sci-fi, and I don't watch that much movies, but this is a good hook. So I think on the side works of fiction, I think I prefer the role-playing games the best. I think we're kind of like running out of time soon. So thank you for the active participation and
sorry that we can't see none of you.
But sure, we let's fix that next year, and we'll be back in as humans and not AIs in the Ropecon. So I think this is it. So I'm quite bad with social media, but I have a Twitter account and I tweet something mostly about supercomputing. Maarja is there too.
Yeah, it's a different family name. Just ignore it.
And I guess that's pretty much it we had in mind. So many thanks for attending, and have a nice continuation of the event.
Yeah, thank you.